So I added some clarifying homeworks assignments. Where we have homework 5, getting started with Bode plots, which are on the main basic shapes of Bode plots we'll go over today. But it's just some simple drawings that if you can do that, basically all the Bode plots are fundamentally from that. Also, there's a midterm 1 practice with some, typical problems. Tell me, describe what that shape is. Bode plot, magnitude and phase. Drive the transfer function, do the Bode plot and the time domain step response. And a convolution type problem. Convolve 2 signals, tell me what it is, and then draw it. Just online, these drawings are a bit rough, so you're not trying to put every point, right? So if 5 tau was 2, right, and it was coming up, right, I would just try to get some. So like if I drew this as a step response of a low pass filter, and 5 tau, if 5 tau were 0.75, then that'd be okay. But if it were 2, I'd have to show some more steps. But it's not a smooth, like I'm just keeping the mouse button held down. Where here I was just doing one click as I got to where I wanted to go. Or if I hold the mouse button down, I can try to do this freehand thing. It's not really about freehand. And it'll show you the answer. And on the exam, you do this in the online, and you do it on a piece of paper that it gets scanned, and I can check to see if you made a mistake in the computer part entering in this, because it can be hard to draw, right? And a little bit hard to see but it should have marked that one all wrong, because I happen to know the answer. So I also put it in the notes, linked in the notes in several I put a link to this in more than one spot, but I thought I would just show you some clarifying videos that tend to come out of office hours. If somebody asks a question and I think maybe everybody needs to know, I'll put it here. And so it can be hard to find things, in an hour and 15-minute lecture, but here's plotting functions from a convolution. So that's review, right? But it shows the basic shapes, and then how to draw a simple Bode plot from basic shapes, or drawing the basic shapes of a Bode plot. All right. Now there's links now back into the notes where they would originally come from, but you might not be getting any notifications. So not necessarily going to go over every detail today, where you should be able to follow the conversation with complex numbers and things like that when we're doing the magnitude and phase. All right. And the first part of today's lecture is that basic shape Bode plot that I think it's 20 minutes or 14 minutes long. So if your transfer function is equal to a constant, like we have here, right? Then to find the magnitude, we would just take 20 log of that constant, and it has no frequency dependence, right? And just as, we have one, or we can have 0.1. Let's start doing some different colors here. We can have k equals 0.1, k equals 1, and then k equals 10, right? So k equaling 0.1 will give us log of 0.1 will be -1. -1 times 20 will give us 20 dB. And since there's no frequency dependence, we just draw a straight line across it. All right. Now, if k were equal to 1, log of 1, right? This is all base 10 is 0. 20 times 0 is 0. So again, straight line. If it's 10, right, log of 10 is 1 times 20, 20 dB. All right. And the transfer functions are not in dB, right? You have to convert things to decibels. All right. Now, what about the phase, right? So phase is the arctan is the imaginary over the real of h of s, right? And the imaginary function just takes the imaginary part. The real function just takes the real part. Hey, Gerardo's, yeah. So, yeah, you could say it would be a different concept. And yeah, it's decibels, deci. That's why we're part of the reason we're in base 10. Okay. Good question, but for Bode plots, I've only ever seen them in base 10. So we don't even write it anymore. All right. So if back to the phase, right? If I'm to draw the phase plane, K is just real, right? So I would draw just a real part, and it would be K wide. So the phase is 0. For everything. Now, yeah, if it was minus K, you'd still get this, but minus K would then be pointing in the opposite direction, and that would be 180 or minus 180. All right, but more on that later. So in our Bode plots, right, this is when we make approximations, right? This is when we have a constant gain. So this is one of the basic shapes: flat, horizontal, no slope. Okay. Now another shape we have is S times K. And sometimes people they know that S equals J omega when we're converting to a Bode plot, right? But sometimes people stop even saying that. They just are going so fast, right? But let's just call it J omega K. All right, let's do the magnitude. Well, it's all imaginary. So we have 20 log the real part of HFs and the imaginary part of HS. There is no real part. And then this is just omega K squared, right? We don't include the J because the imaginary part just strips out the part that's scaled by J. And this gives us 20 log omega K, which we can also put as 20 log omega. And the reason why you might want to do this is, yes, it's multiplied by 20, right, log, but we're progressing in a logarithmic fashion. So really we're getting an mx plus b type of function. And the slope in this case is 20 decibels up for every decade over, right? So if this is a decade over, right, 20 dB up, that's 20 dB per decade. Now, so essentially, just to give you a heads up, we're going to have a straight line, right? The slope in this case, it's going to be 20 dB per decade. And then whatever the gain is going to shift that line up and down. But really, if I look here, what's easy to do is where will it be 0 dB, right? So if K is 0.1, right, what omega makes 0.1 1? And that'd be 10, right? So if omega is 10 and K is 0.1, all of this is 1 and it turns into 0 dB. So right here is omega equals 10. So I know that that's going to be 0 right there. And now all I have to do is go over 1 decade and go up 20 dB. And then I can draw it in the other direction too. Right, down 1. So that's 3 decades and 60 dB. All right. Now, what makes omega k equal to 1 when k equals 1? 1. So 10 to the 0 is 1. That means we're going to be at 0 dB here, right? And because I have experience, I know that these lines are all going to be parallel. So I can just draw it like that. And then 10, right? 0.1 times 10 equals 1. So I know this is going to be where it's 0 dB. All right. And so this is K, this is, excuse me, S10, S times 1, and 0.1 times S. Now the phase, well, when we were working on the magnitude, I said the real part was 0. So it's, if I were to draw the complex plane, right, here's the imaginary part, here's the real part, and it's really omega k, whatever omega and k are, it's pointing in that direction. And so that's 90 degrees. And the phase would be there. Okay. Now, sure, if this were minus here, then it would be minus 90. Then I would subtract 180. All right. The reason why I wouldn't add 180 is you're trying to keep the phase number as small as possible. And when you're working with CAD tools, they have algorithms to do that. Now, K over S. And this is my shorthand for, this is the real part, and that's the imaginary part. So here it's all real. Right here, it's all imaginary. All right. Now, what we do is this, and this will help us find out where things will be zero. So this actually shows that it's minus 20 dB per decade, right? Because I can actually that would be my B part, which would shift it up and down. And then this is now I'm getting a minus slope. But actually starting here makes it a little bit easier. So if K were equal to 0.1, right, what omega would make it equal to 1? Well, that'd be 0.1. If K were 1, what omega would make this into 1, thus 0 dB? 1. Same with 10. What omega would make this relationship go to 1, thus 0 dB? Here, right? Then I can look here, right, and know that I have minus 20 dB per decade. This, by setting where 0 dB was, I've done my offset. Okay, it's a lot easier to do than, here's the slope, and then finding a place where this is on the offset and going. You just look at it and know that this is going to be a line going down, and you just need to know where it crosses 0 dB. All right. So I want to kind of repeat myself is I can show you where things come from, but really, if you see this, if your equation is reducing to this, you just know it's a straight line, and you know that it's minus 20 dB per decade, right? And then you just find out where this is equal to 1, and that gives you your 0 dB. All right. I'm just going to scroll a little bit. So for the phase, we have the arctan of the imaginary of the numerator, the real part of the numerator, minus the imaginary of the denominator. All right. So just recalling, we had K over J omega because S equals J omega, right? So the numerator, it's all real. So it's 0 K, right? Here, it's all imaginary, right? So it's omega divided by 0. Again, this is all real. So I just have a vector going that way, 0 degrees. Here, it's all imaginary, right? So it's 90, but we subtract it. So that it's the phase is all minus 90. All right. And we have so in the notes from, they're in the notes from last time, linked from this time, where what if S is, not 1, but raised to the second or the third power, right? It just changes the slope. So if we had K times S squared, it would be 40 dB per decade, right? Then you have the offset. The phase would be 2 times 90. What omega would cause it to be 0 dB, right? You just solve for it, okay? And then for K over S to the N, right, minus 20 dB per decade times N, the phase is minus N, however many order of magnitude you have, or I mean, order of the function. And then K is, that's always what it is. So I showed you when S was raised to the power 1, but it could easily be raised to the 2, 3, 4, 5, 6, right? And you can just use that chart. So it's all kind of based on that. So let's try to tie this together. Now I write these equations so that I always try to put the gain here so you can kind of see what it is, right? And then here, the cutoff frequency, omega C or omega naught, is 0.1. And notice how these are the same. The numerator has no terms of S, and the denominator has one term to the order, first order. All right. And so this is a low pass filter. All right. So what we need to do is, turn that into something K, SK, or, K divided by S, because we know we're going to be flat, up, or down. All right. Now, the key is this omega naught here. All right. That is, there's a pole at minus 0.1 or minus omega naught. So seeing that right there, when S equals that, right, and this is for real poles and zeros, right, I know that something is happening at 0.1. All right. So I know that that's going to be the first thing I need to do. So now I can say, well, what if omega is much, much less than 0.1? And now here's the thing. Sometimes people will say, what if S is much, much less than that? And it kind of works out because we're talking about real roots. But ideally, we're talking about omega. But again, the assumption when we're on a Bode plot is S equals J omega. And we've actually not using Laplace anymore, but we're using Fourier. So what happens, right? If 0.1, and now I'm just going to put J omega plus 0.1. This doesn't change, right? But if I were to do the magnitude, this would be omega squared plus 0.1 squared, and I'd take the square root of that, right? But I don't have to get that far yet. If this is so much smaller than that, this drops out, and I get 10 times 0.1 divided by 0.1 equals 10. So I have this, which is, I'll just tell you now, it's a low pass filter with a gain of DC gain of 10. But when omega is a lot less, is a lot smaller than 0.1, it reduces to 10. Well, that's k equals 10. Log base 10 of 10 is 1 times 20 is 20 dB. So let's just draw that. And this is an asymptotic plot. So I'll just draw it, forever. All right. Now I'm going to do a little math down here. We'll switch to green. Now, what if omega is much, much bigger than 0.1? All right, so I have 10 times 0.1. Now, omega here is so much bigger than 0.1. Really, I'm going to have J omega, because remember, this is so much bigger than 0.1, it's no longer there. Well, now 10 times 0.1 is 1. And then I have omega. So that's really like 1 over S. So I have a straight line down. Where's 0 dB? When omega equals 1. So let's put that here. Right, that's 0 dB. And it's a straight line with a 20 dB slope per decade. So that's down 1 over a decade. Down another 20 dB over a decade. All right. And then I can go this way. Now there's a little bend there because of my drawing. So these are two asymptotes. This is when omega is much, much bigger than 0.1. This is when omega is a lot smaller than that. And then the way we take the final plot is we just take those parts. So that's when it's smaller, that's when it's bigger. And that would be the magnitude. All right. Now the phase can be a little trickier. And while there really is a basic shape of horizontal and down, there's really 3 things that you think about. And that's really when, I think you'd rather not have yellow. When omega is much, much less than 0.1, or really omega is greater than or equal to, less than or equal to 0.1 divided by 10. And this is just given because I'll try to show you later why it's given that way. So that's one condition you have to take into account. Then omega equals 0.1. That's another condition. And then that's the third condition. Now, Yeah, with the magnitude, we had one pole. Right? And all we had to do was worry about when it is a lot less than and when is it a lot greater than. We got two asymptotes and then just connected them together. All right. Here, we're effectively having a phase asymptote here, a phase asymptote. And this is actually a single point, and then you draw a line between them. All right. So let's look at the phase. So if omega is a lot, if it's a lot less than one, then the assumption being it's just a tenth, right? Then what happens? Well, this j omega drops out, and we get 10 times 0.1, 0.1. What's the phase of this? 0 degrees. It's all real. What's the phase of this? 0. It's all real. 0 minus 0, 0. So in this case, the phase is 0. And I can just draw, a line like that. But this point here, a tenth of 0.1. So this is 0.1. That's a tenth of 0.1. That's going to be an important spot. Now, with the phase, what about when omega equals that? All right, so I have 10 times 0.1, and that's still going to give me 0 degrees phase. Nothing changes. But here, if I have j 0.1 plus 0.1, right, and I draw that, 0.1 real, 0.1 imaginary, that's 45 degrees, right? But it's in the denominator, so 0 minus 45 is 0. So you put a point here, right? You don't really, well, I'll just show you, but you just put a point there. Now here, when omega is a lot, it's greater than or equal to 0.1 times 10, which is really saying omega is much, much greater than 0.1, right? This term is now dominating, the imaginary term is dominating the real term, and it becomes 10 times 0.1, which is still 0 degrees phase. And then it goes to j omega, right? Which is really 90 degrees. 0 minus 90 is minus 90. And so I get an asymptote here. Okay. So here is omega much bigger than 0.1. Here's omega equal to 0.1. Here's omega less than 0.1. And the 10th, so if you find the minus 45 degrees phase part, go over 1 decade or a 10th, all right, that's where you'll draw your first line. Okay. But then I have this asymptote and this asymptote. I'll switch to yellow. Bigger brush. Comes here. So that's less than 0.1. Now I'm on this track, right? And now I'm on that track. So the phase goes from 0, passes through 45, and then goes to minus 90. All right. And the thing is what if I had h of s equal to 10.1 to the n, s plus 0.1 to the n? What ends up happening with the phase is that if this is 2, this point becomes minus 90, this goes to 180, right? If it's 3, it's 45 times 3, 90 times 3, right? And then on the magnitude, right, if it's 1 over s, it's 20 dB per decade. But if it's 1 over s cubed, then it would be minus 6 dB per decade. And what I'm saying is, if I drew this, call that omega, call that omega naught, right? The only way, you'd really know the difference is that this would be n. The larger the n, the steeper this slope would go, right? But the way I've drawn it is it doesn't affect where omega naught happens, and then the gain is out here, so that's not affected. And then the phase, there's omega naught divided by 10, and there's 10 times omega naught. That would be 0, and that would be minus 90 times n, minus 45 times n. And so that this low pass shape, right, it's the same if you have one root or repeated roots, right, that are the same. Now, there's an example when the roots aren't the same. That's a little more complicated, but well, let's go back, point something else out. Right. This was for omega naught equal to 0.1. But what if I had omega naught equals to a k? Well, I've actually drawn this shape, and the easiest way to do this would just be say omega naught is a k, that's 10, 100k, and then here is 100. Same thing, 1k, 100, 10k, and I would just rewrite the axis. What if omega naught was 2k? Oh, well, wait, how's that logarithmic go? All right, 1, 2. Well, if I was just drawing it by hand, I would just put 2k, 20k, 200k. I would just scale the axis, but it's the same shape. Okay. So here we have a high pass filter, all right, because there's two roots at 0, meaning since it's squared, if I enter in a 0 here, h of s goes to 0. It's repeated, so I have two of them. So those are roots. And then I have a pole at minus 100. So when I am going to plot this function, right, I have one pole and two, oh, that should be squared. I have a repeated pole at 100, and I have a repeated 0 at 0. Now, the trick is this is logarithmic, so I can never actually show 0, all right? But basically, I got something going on at 100, which is here, right? But I won't really be able to show the whole plot. So I'm just going to put 100 in the middle, right? And that'll be 1K, and that'll be 10K, and this will be 10, and that'll be 1. So when you're drawing your plots, when you're doing it on My Open Math, you can't do this kind of trick, if you will. I do not know how to program you to put in your own axis, or for it to actually take a hand-drawn plot and tell you if it's correct. All right. I don't know how to do that. Anyway, something's going on here, right? And with the phase, right, we know that we have something going on at 100. We know we have something going on at 10 because 100 divided by 10 is 10. And we know something is going on at a K because 10 times 100 is 1K. So now we kind of have a little bit idea of what's going on. So let's do the magnitude. And so this is 0, which we can't really plot. So we just know that, you know, omega is going to have to be greater than 0. We'll just keep that in our mind. But we do have a pole repeated at minus 100 radian per second. So let's just do it. What if omega is a lot less than omega naught? Okay. Then we have the 10 is there, right? We have j omega times j omega. And this would be a lot smaller than 100. So then we have 100. Which becomes 10. Now, the phase you might think is a minus 180, but in fact, it'll be 180 because this gives 90 degrees of phase. This gives 90 degrees of phase. And so it adds up to 180. So if you use LT Spice or SciPy or anything like that, this transfer function will give you a phase of plus 90 in this region. All right. So what I see here, right, because remember the magnitude will strip out that minus sign. I see omega squared. So that's going to be 40 dB per decade, right? But where is it going to cross 0 dB, right? So I want omega squared divided by 10 to equal 1. So omega squared
Professor, isn't that need have to be 1,000? Like omega
no,
square over
no,
1,000 because
yeah,
100 squares.
hold on. Right, sorry, thank you. No, it was just on me that that wasn't working. Okay. All right. Yeah, thanks. So it's still 40 dB per decade, right? I still don't like it. And in fact, just know that it's 40 dB per decade. All right. Because what is I usually like it to work out. So I would have had this as 100. Okay. But since it's 10. So I'm actually, I know that line is going to be that. Now what I'm going to do is, what if omega is much, much bigger than omega naught? All right. So that is going to be 10 times j omega times j omega. Right. And then here, j omega is a lot bigger than 100. So that this will turn into j omega because the 100 drops out. Right. These all cancel out. So it's 10, right? And so that's just a constant, and that's just going to be 20 dB per decade. And then, and this is, I'm saying how I do it, is that now I found that high gain, I can draw an asymptote, right? I know it's going to change at omega naught, right? But it's going to be down 40 over 10, down 40 over 10. Okay. And now you can see, it's crossing 0 dB, not exactly on one of my grid marks. So then the complete Bode plot does this. Okay. Now, yeah, it's true. I could have gotten the offset by where omega squared equals 100 squared divided by 10, but it wasn't coming right out where I wanted. It was coming out not a nice power of 10, which is why then I switched, knowing that it will change direction at omega naught. So I don't exactly have to find where 0 dB is. I just know that this line, right, is 40 dB per decade. Right. And now the phase So here's the thing. This, it's all real. So it's 0. Now here, you might say that turns into minus omega, which is a vector pointing that way. And since it's negative, I should get minus 180. But really, it could be minus 180 or 180. But in engineering, we're saying this turns into plus 180. And the way to remember it is not to use the complex math straight out, is that convert this to phase, right? So that would be omega squared 90 plus 90. And so that's how you would get the minus 180. Now, yeah, if this were multiplied, the whole thing were by a minus, at that point, then you can change that to minus 180. All right. So I just converted it into polar, right? And so even though omega is changing, the phase in the numerator isn't changing because it's not in relation to a real part. So it's still 180. All right. But here, right, we have 100J plus 100, 100J plus 100, which converts to 45 and 45. I sum that. Right. And now I get 180 minus 90 for 90. So at 100, my phase should be 90. And I'm just going to call this 180. And it doesn't change until 1/10 of 100, right? And it doesn't flatten out until 10 times 100. Now, why is the phase 0? Right? If omega is much, much greater than 100, I still have, since we're caring about phase, right? We have 10 omega 90. So it's still 90. But now the real part is no longer important. And so I have an omega at 90 times an omega at 90. And you can see that the 180 is, this becomes 180. 180 minus 180 is 0. All right. Now, what there are so many permutations of this, all right, that it can be quite hard to do it in several class times. All right. But what I've done is, this is just a blank sheet. You can grab and use however you like. You can draw on it. Python code is linked. But there, what I want to draw your attention to are these notes. All right. Where it even includes the review, right? And it's giving examples of minus 100s, right? 100 times s squared, so things going up. All right. Just like I did in the example, I have this, and then omega less than 1 equal to 1 greater than 1. So that example, this is just a s plus 1 where there's a root at minus 1, right? That's what that looks like. Then here's the integrator. Okay. Then here's the 1 over, we have a pole at minus 1. So it's all kind of there, right? Where here's a low pass filter with a gain of 1. Here's a low pass filter with a gain of 10, right? Because hey, what happens at DC? I'll take S out. 1,000 times divided by 100, it's constant, so I know the gain, right? Now, yeah, if I let S equals 0 here, right, it all goes to 0, right? Then if I let S goes towards infinity, it's S squared divided by S squared, they cancel. And then I get an AC gain of 25. So I'll be up in here. Now this one's a little more complicated. How to put it? You might see this in life, but you will not see it on the midterm. All right. But if you can do this, you can do just about anything. All right. So I kind of went through different and simpler examples, but this has, those notes pretty much have almost everything you'll run into. All right. Now, I have to point something out. There's a lot of texts that will transform this into this. All right. And now it's S divided by 10, much, much less than 1, equal to 1, much, much bigger. And what they'll say is, oh, this part right here, 100 divided by 10, that is the DC gain. All right. And it is true. All right. However, this does not work for this. So I convert it. I have my 100s. I take out my 10. S divided by 10 plus 1. And then folks will circle this and say that's the DC gain, but it's not. It's all multiplied by S. So when omega is equals 0, this is equal to 0, right? This is a low pass filter, right? And you don't need to modify anything. You know that that's omega naught right there. So all I would put is 10, 100, 1K, 10K, and that's 1.1.01. Right? So something's going on here, right? And yeah, if I just let S equal to 0, 100 divided by 10 is 10. It's 20 dB. It changes direction at 10, right? Now for the midterm, this kind of sketch, I guess what it is, you'll do it in the computer, but then you'll also do it on paper that you'll, or like in some manner that's handwritten, right? That I'll check to make sure that there wasn't some typo when you entered it in. Okay. Because people make typos in my open math all the time. It helps me grade, but I don't want anybody's midterm grade to depend on whether you accidentally put a typo in or not. All right. In this case, something's happening at 10. So again, it's 10, 1.1. Okay. But I know that this is there's a root at 0, and I have a pole that isn't at 0, because otherwise it'd cancel out. So I know this is a high pass shape, right? So really, rather than setting S equal to 0, I set it to infinity, and I get 100 divided by 10. So now it's 20 dB. Oops. And I have 20 dB per slope, per decade slope going up. And what can happen is people will do this kind of thing. You know what? I'm not going to show you the wrong thing, but it's really weird. And it comes out because somebody did a nice video on an example more like at the end of the notes. All right. Where he sets omega equal to 0. He pulls everything out and then calculates the DC gain. And it works even though there's roots, because the roots aren't equal to 0. So what I'm saying, the video is correct for the example he does, but it doesn't work when you have a root at 0. And really, we have so far high and low pass filters. And since we're electrical engineers, that's what we're going to use. Go back, right? I could easily make a random number generator with so many roots and so many poles, and then you just randomly do it. But I try to make the questions that you're going to be asked things that'll be similar to what you would use or that you would see on a job interview. So I kind of limit the number of things I'll ask. All right. So that's, and what it is when I'm grading, I can tell when people have watched that video. My other problem with this technique, right? I mean, it's mathematically correct, but I've seen people make these mistakes because it's one more thing you have to do. Here, right, there's a transfer function. S is less than 10, what happens? S is a lot bigger than 10, what happens? Right? So you don't have to manipulate the equation any, right? It's, what I'm saying is when I'm grading, if you use this kind of pull out the pole kind of thing, the chances of getting it wrong go up. But I can't predict any individual performance. All right. So I'm just asking you to, well, think about it. I'm not going to tell you, because if you get it right, you get it right. I'm in this uh thing, I'm not testing a particular technique or doing it my way. It's just I got to say my way is based on teaching since fall 2016 this class. All right.
Professor,
Yes, sir.
yeah, if so, you mean if you use omega like I mean, if you use to find the asymptote, you check omega equal to 0 and then omega equal to infinity, you will not have it or what?
Well, it's really, that's like a shorthand. It's like omega a lot less for magnitude. It's omega a much less than omega naught, and it's omega much, much bigger than omega naught, which can be infinity, which can be 0, right? And so when I start speaking quickly and say S equals 0, oh, that drops out, but the whole thing is 0. So it's just very small. And then when I let S go to infinity, it goes to some constant value. If I kept taking this out, it would keep going smaller and smaller, right? I could get close to 0, right? I could have omega equal to 1 nano radian per second, right? I could never measure that, but it'd take too long. But that's really what's going on. And for phase, it's, you have the same two conditions, but you also have where it's equal. And it's in here, the magnitude, everything happens from omega naught. Here in phase, it's omega naught divided by 10, omega naught, and 10 omega naught. So that hopefully you, now when you're saying, oh, omega's between these two values, because that's the other, it can be excuse me. What if the poles aren't repeated? All right, you have this. And so it gets a little trickier, right? But I know, right, I have no roots, but I have a pole here. So something is happening at 10 and something is happening at 1,000. And that's magnitude. And then for phase, well, I have 10, I have 1K, but then I have something at 1 because that's a 10th of 10. I have something at 100 because that's a 10th of 1K. And I have something at 100 the other way. And then I have something at 10K. And these two should be at the same point. So I just know by looking, these are where the action is. All right.
So
But in this, yes,
it's actually 10 or minus 10.
I mean, the pole is minus 10, but the cutoff frequency is 10. Right. there's a pole at -10, pole at minus a K, but these breakpoints, right? That's a good question. Because now I think you're maybe, I said it before, but it could have been going fast. It's so that if I have H of S 10 times a K, S plus 10. Right. I have a pole here at -10, and I have something out here at 1K, obviously not drawn to scale, but this axis here is the real, and this is J omega, right? So I let S equal J omega, but we really just say omega. So we take this axis, right? And we just flip it 90, right? And then as we're sweeping omega, right, these poles are changing where it breaks. Right. So I'm moving along this axis, calculating, right, the real of HS squared plus the imaginary of HS squared. Okay. And now, if these are the frequencies, if I have a radian per second sine wave, right, this will give me the magnitude of the output signal, and then the phase would still be 0. And so sometimes you'll hear people will say there's a pole at 10, 1K. Not really. We know the poles are negative, right? But these are the break frequencies. And we convert this to log. And that means then right at 0, we can't see. Does that help?
Yeah, thank you. It makes sense now. So everything is
Okay.
going on the first quadrant and the third quadrant. No,
Well, let's
fourth.
just
First and
say
fourth.
it's on the J omega axis. We're taking real and imaginary information and converting it into magnitude and phase information.
Yeah. All right. Thank you.
Yeah, listen, I know some people will be listening. I did put in some extra homeworks to help study for the exam. If you got to go, you got to go. I'll just record where it is and you can watch it later. But you should have gotten a notice. So midterm practice, we'll have some practice midterms. And then homework 5, getting started with Bode plots. That's really just the shapes going up and down and getting used to it. And if you can get those shapes, then it's easier to construct the others. Okay. That's it. That's all I have.
Professor,
Yes,
so the roots are where the frequency changes, that the whole concept.
roots or poles, actually.
Okay.
So it's just if I had S plus 10 and then S plus 100, well, now I have a root at minus 10, but basically something's going to happen at 10 and something's going to happen at 100, right? And so let's just say, what if omega is much, much less than 10? All right. So I'm going to have this left over. So if omega is a lot less than 10, it's a lot much less than 100. So I'm going to have 10 divided by 100 or minus 20 dB, right? Now then, what if I'm greater than 10 but less than 100, right? And then what if I'm much greater than 100?
100.
Right. So if omega is bigger than 100, well, then it's bigger than 10, and it's going to be S divided by S. And so it's going to be 0 dB, right? Now, yeah, in between, right, it's going to do something like this.
Okay.
And so it's like I know that it's flat here, and I know that it's flat that way, and I know at 10 and 100 it's changing direction. But if it's bigger than this, then it goes to S. But bigger than this is not less than that. I mean, these two are still active, right? And so S compared to omega would be small, and you'd have S divided by 100. And so that gives our S shape, and the 100 is setting the offset so that it hits it here. But it's so much easier to know, yep, that's where it flattens out here, and then draw a 20 dB line per decade line there. Okay.
All right. Thank you, Professor.
All right. But really, we're looking for this exam, high, low pass filters. And then there's one low pass and high pass with two different breakpoints. Okay. We'll get into that next time. All right, everybody. Take care.